negative 2.308 meters per second.
Sine of 5.77 radians per second times time.
How did you get the negative 2.308?
From what we had done before, that if this is my position graph, that our position function, this is my velocity, it's the omega comes out, so I get negative omega, a omega. It's a hand wave of an explanation, but
I gotcha.
you take the first derivative of this, you get that.
Okay.
So, how fast is it, what is its maximum speed?
.308 meters per second?
Yes. There's my maximum speed right there. It will happen when this is equal to 1 or negative 1. At what angle is sine equal to 1? I need more than that.
90 degrees.
Okay. Or in radians, since we're dealing with radians here.
Pi over 2 radians?
Yes. So this would, at a maximum of 5.77 t, is equal to pi over 2. So what time is that?
Just about it. So,
1.57 seconds.
No.
That's just pi.
That can't be right. That's just pi over 2.
Oh.
31.37.
No.
No,
Not
I
that
got
big.
9.06. Hold on.
I got
You get pi over 2, about 1.57, then divide by 5.77.
Okay. I got
0.27 seconds.
Yeah.
0.27.
There we go.
All right.
I was right the first time.
There we go.
I was pressing the wrong button.
So the mass we pulled down from here is getting forced upwards because it's farthest from its equilibrium position. It gets pulled up, it hits the equilibrium position, so it's no longer gaining speed anymore. And once it passes it, it starts to slow down. It's going to slow down until it gets, and then it'll stop, move back in the other direction, hit equilibrium, and then slow down again, and then speed up. It's basically oscillating back and forth. Not only basically, it's oscillating back and forth. Now, what is the period of this oscillation? We have a formula. There are other ways of getting there, but what is 2 pi times the square root of m over k?
.09
Yeah,
seconds.
that's what I got.
All right. How can I get 1.08? There's a rounding off. How did I get that? Because I'm not doing that square root and pi in my head. think about what we'd already answered. We figure it takes 0.27 seconds to go from its farthest down to equilibrium. I'm assuming 0.27 was a round down.
That was,
Right.
yeah.
So it takes 0.27 seconds to get from here to here. How long do you think it's gonna take to get up to its maximum position?
Same amount of time.
Yep, and then back to here,
Same amount of time.
and back to here.
Same.
In other words, all I did was multiply that times 4. So let's now figure out what that maximum speed is a different way. Oh, actually, let's do acceleration while we're here, and then we'll find out maximum speed a different way. My acceleration is negative a omega squared cosine of omega t plus 5. I know this part, so that's cosine of 5.77 t of radians per second t plus 0. So it's a omega squared.
Negative 13.32 meters per second squared.
So let's think about our situation here. I pull it down, I let go. I know that acceleration is equal to force divided by mass. I stretch it down 40 centimeters from here. And so this is K of 100 newtons per meter. Let's stick in the letters first. So this is K delta X over M. So it's 100 newtons per meter times 0.4 meters divided by 3 kilograms. What do we get? We're around 13.33.
Yes.
Units?
Meters per second squared?
Oh, yes, sorry. Brain burp, all right. There's a rounding difference between these two. But notice we get the exact same. We get the same answer. When I just figured out acceleration here, I did force divided by mass. What did I ignore? What are the forces acting on the mass? I heard weight and,
Is it, I don't know. I know it's weight and then force.
yeah, spring force.
Okay. That was just.
But weight's not showing up anywhere in here. Matter of fact, if I put weight in here, well, let's run through that. Let's say I still need this. We'll assume that's etched in people's heads. If I did K delta X minus the weight, because it's pointing in that direction, over the mass, I get K, that was 100, times delta X, 0.4, minus 3 times 10 divided by 3. what do I get?
Oh.
It will be a different answer, I'll tell you that. 3.3?
Yes.
So it seems like I should be able to get the same answer. And it comes down to if I'm taking weight into account. If I take the weight of this mass into account, then the distance that it's stretched is actually from here. So if I bring weight into it, that 0.4 is incorrect. It is, this would be 0.7. The distance that goes from here to here. And so now I end up with 40 divided by 3, which is 13.3 meters per second squared. This is to show that if I can treat this as if the gravitational force does not exist if I treat this as equilibrium and I look at the displacement from here. Because this takes the weight into account already with the fact that it's stretched that far. If I want to bring weight into it, then I have to take it from here before I put the mass on it at all. Exact same, there's videos where I derive that. The exact same applies to looking at it from an energy point of view. And so let's find the maximum speed from using energy. Questions before I erase any more?
I think I'm still a little confused on the negative side because the standard, like in the F equals negative K times displacement, that standard equation is for if up is positive.
Right.
Okay, and because we made down positive,
Oh.
we got rid of that negative in the K.
If down is positive, then my acceleration is, I know my acceleration's up because I pulled it down and I let go. So technically, if I want to go with down is positive, this would be W minus K delta X is the force because weight's in the positive direction over M, and that's equal to negative A. Because I'm looking for a value of A, which is, I'm looking for a positive value.
Okay.
So that's, if I stuck to the original convention, that's the way I would have written it, which basically multiply both sides by -1 to get this.
All right.
Is that sufficient?
Yes.
Okay. Gil, you about to ask?
Yep.
Okay. All right, energy point of view. Again, if we want to bring gravitational potential energy into it, then we are looking at this as a starting point. If we want to ignore the gravitational effect, you start with this as the starting point. So let's ignore the gravitational effect. I know that initial energy equals final energy. And I know this because the only two forces acting on this are the gravitational force and the spring force, and both are conservative. I have kinetic plus potential equals kinetic final plus potential final. I'm about to ask the question. Prepare yourselves mentally. Chorus of angels, that's what I'm shooting for. What's the formula for kinetic energy?
1/2 mv squared.
You got it? What's the formula for potential energy?
MGH.
1/2 kx squared.
Try that one again. What's the formula for potential energy?
Did you have it, Sarah? I was gonna
I
say
know it starts
MGH.
with 1/2.
No, the proper response with that generic question is which one?
Which one?
Oh.
The one associated with the spring. Now, Sarah.
1/2 kx squared.
Great job, Sarah.
Oh, yeah, you're right. That makes sense.
If we wanted to do the longer stretch, then we would also have gravitational potential, so MGH would be appropriate if we are establishing this as our starting point. What's going to be equal to 0?
The initial velocity. So the first, yeah,
Speed.
yeah.
Because V initial is, that's 0 because V initial is 0 meters per second because we pull it down and let go. We're trying to find the maximum speed, and the maximum speed is going to occur also when that is 0. V max when U equals 0. And so it just simplifies down into just that. The initial potential is equal to the final kinetic. The 1/2 cancel out, so I'm left with 100 times 0.4 squared is equal to 3 times V squared, V final squared. So that is 16 is equal to 3VF squared. VF is equal to the square root of 16/3, which seems like it's somewhere around 2.309? I'm doing it off memory. I don't think I wrote it down. I erased where it was. And these boards are too new for me to read it off of.
2.309.
Is it 2.309?
I got 2.308.
Wow.
Oh.
Somewhere in that ballpark.
Yeah.
And that's what we got before. All right, questions to hear? All right, why don't we stretch legs for about a couple minutes, and then we'll come back and still stick with waves, but we'll do something a little bit different. Come up with a justification for my not putting this stuff away.
Put that one down more now. Oh, perfect.
By putting the mass on here, I'm increasing the normal force between the table and the base. By increasing the normal force, I'm increasing the friction. All right, so I have mass on the end over there. Let's plug this back in. There we go. Just as predicted. Hopefully you saw the wave pattern there, that you saw the places where it was vibrating a great deal and places where it was not vibrating much. The places where it's not vibrating much, or ideally not at all, are called nodes. The place where it vibrates the most is an antinode. 60. So what's happening here is this thing is vibrating up and down. This is called a string vibrator. As it vibrates up and down, it sends a wave down to this end. And what happens when a wave hits a boundary?
It bounces back.
And what is that called?
Reflection.
Yes. Now, in some cases, it will continue on. So usually, when a wave hits a boundary, two things will happen. One, it reflects, and the other one is that it will propagate through. So it loses energy when it does that. So when I have a wave being sent down this way, it hits this, it reflects back the other direction. So I have waves traveling in both directions. And so the big question is, what happens when the waves meet? Is that bigger or smaller? All right, so I have these points, and I don't know how well you can see that with the white background there. Push that up. Perhaps a little bit. Is that any better?
Yeah.
All right, so I have this point right here, which is not moving much at all, and I have this point right here, which is moving a great deal. The antinode, that's a node. There's a node here. There's a node there. This is a sine wave generator, so I can change the frequency. Typically, this is plugged straight into the wall, in which case this is vibrating up and down at 60 hertz. Right now, it's vibrating at 61.7 hertz. And if I increase the frequency,